right, so today what we're going to be doing is we're going to just do one more quick example of this related rate stuff, which is going to be a little bit different than the ones that we've seen before. In fact, it's going to be a little bit weird because it's going to be, the example we're going to do is one that often I think gives students a lot of trouble. And I'm not sure, to some extent, I think it's because of the setup, which can be a little confusing for people sometimes to see exactly what's going on. But another part of what I think actually makes it confusing is that it's almost too simple. So you look at it and you think it's got to be more complicated than that. And you kind of end up throwing yourself off by trying to make the problem harder because it seems like you must be doing it wrong if it's that easy. Actually, it's just a really simple situation that for some reason it's difficult to write it down. So let me show you an example of the kind of problem that I mean. First of all, of course, we're going to need some space on the whiteboard. And then we're going to need a working pen. And this is, again, one of these things I should probably do before I start recording, but, whatever. There we go. Okay, this one seems to be working all right. So here's a situation. Let us suppose that we have got a lamppost. And we're just going to draw this picture rather than me trying to write a paragraph explanation of what's going on here. So this is a light. I don't know if that really looks much like a light, but you know what it is because I tell you what it is. Let's suppose that this thing is 20 feet up in the air. And what we have is we have a lady who is walking along here. There she is, sort of. Stick figures are the best I can do. And let's say that she is 5 feet tall. I'm gonna pick 5 feet just to make things easy. I know, just whatever. And she is walking along to the right. And let's say that she is walking at 4 feet per second. And our question is, so the light is coming down here and she's gonna be casting a shadow. And what we want to know is, how fast is the end of the shadow moving? So let me write that down. That's not how you spell shadow. And then let's also ask, how fast is the shadow's length increasing? So that's a slightly different but very closely related question. One is the question of how fast is the end of the shadow actually moving along the ground, but then there's the question of how fast is the shadow getting longer? Because as you walk away from a light, you're going to be making your shadow get longer, right? As we increase this, it's going to end up this line here that's casting the shadow is going to be less steep, and this is going to result in a longer shadow. And this pen is now having issues, so maybe this is going to show up a little better. No, that doesn't really look great to me either. All of these pens are terrible. Why are all of my pens terrible? Okay, this is a good pen. Finally, a good pen. Okay. Here's the situation that we're going to set up here. There are two right triangles involved here. There is the triangle that goes to her head, and then there is the triangle that goes along the ground and whose vertex over here is the end of her shadow. So one of them has a vertex at the top of her head, one of them has a vertex at the bottom of the ground. Here is what we are going to be able to do. I am going to label this length as x. So x is the distance that she is away from the lamp post, whatever you call those things that cast light with a lamp on the top of them. So x is this distance here. Now, what do I know about the height of this triangle? Well, it's actually 20 minus 5 feet, which is 15 feet tall. And then I'm going to call this length here L. So L is going to be the distance from the base of the lamppost all the way to the tip of the shadow. So what I'm asking here, how fast is the end of the shadow moving? I'm really asking, what is L prime? Now, in order to ask how fast is the length increasing, well, that's going to be L prime minus X prime, because it's the difference between how fast is the end of the shadow moving versus how fast is the woman moving. In other words, how fast is her location changing? That difference is going to give me how fast the shadow's length is changing. So what can we say about these relationships? Well, here's where things get both weirdly simple and get strangely complicated to kind of figure out. Because it turns out that this relationship is really, 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 really simple. Okay, and the reason that it's so simple is because these two triangles that I drew, these are actually similar triangles. Well, what is the nice thing about similar triangles? First of all, what does similar triangles even mean? Reminder, it means all of their angles are the same. Well, that's fairly obvious in this case because they're both right triangles and they share this angle with the lamppost. So yeah, all three angles have to be the same. But the nice thing then is that the ratios of corresponding sides have got to be the same. That means that x over 15 has to be equal to L over 20. Another way of putting this is that 20x has to equal 15L. If I differentiate this with respect to t, I'm going to get that 20x prime is equal to 15L prime, which means L prime is going to be equal to 4 over 3 x prime. But what is x prime? Well, she is moving at 4 feet per second. So this means that L prime is going to be equal to 4 over 3 times 4, which is 16 over 3 feet per second. So that is how fast the end of her shadow is moving. 16 over 3 feet per second. Now notice, weirdly, this doesn't even depend upon where she is. In most of our related rates examples, we found that the rate depends not just on the other rates of change, but also on the values of the variables. You go back to look at the examples last time, I think every single one of them was like that. This time, there's no actual dependence upon what X or L happened to be at the time. It's literally all just dependent on X prime. So then, how fast is the length of the shadow changing or increasing? Well, that's just going to be 16 over 3 minus 4, which is going to equal 4 over 3 feet per second, which, of course, I don't really have any room left on here to write it down. So here is our answer for how fast is the shadow moving. Here is our answer for how is the length increasing. So like I said, for some reason, these types of problems, these lamppost similar triangle problems, often give students a challenge, but in one sense, they're almost kind of the easiest related rates problems that we can do. In fact, you don't even really need calculus to see that this is what must be happening, because if this ratio is always going to hold, well, then this means that L is always going to be equal to 4 over 3x. Since L depends linearly on x, any change in L produces the same change. Any change in x produces the same change in L no matter what. That's the defining feature of linear functions. And so we don't even need calculus to be able to say, oh, well, any change in x produces 4/3 that much change in L. That means the rate at which L is changing has got to be 4/3 the rate at which x is changing. Like, we could actually have figured out this problem without even really thinking about limits or anything like that. Now, technically, yeah, to make that precise, you need to phrase it as a limit. But, like, people could have guessed the answer to this problem and made a justifiable guess in some sense, like a reasonable, you could have reasonably figured out that that must be the answer, even if you couldn't quite prove it without referring to limits, but you could have figured out that this is what it's got to be. There's no other possibility that would make any sense. Anyway, I wanted to show you this example, and even though in one sense I feel like this is one of the simple examples, I'm showing it to you last because, like I said, it's almost deceptively simple, and students tend to find themselves getting into trouble kind of making it more complicated than it needs to be. So don't overcomplicate your problems. All right, so now that we've done this last example of a related rates thing, we want to talk about the last things sort of that we're going to be covering in chapter 3, and these are going to be differentials and linear approximation. So first of all, let me tell you this. Your book lies to you about what differentials are. What they tell you that differentials are is kind of, sort of, what they sort of work out to be in practice in many situations, but it is not strictly speaking true. And I'm not going to tell you exactly what differentials are either. The reason for this is because in order to make sense of differentials, we first need to, like, if you really want to rigorously define what a differential is, you have to actually first start by defining what a tangent vector is, and then we define the differentials as the dual functions to the, we define it as the duals, something called the duals, D-U-A-L, to the tangent space, and it's complicated. But I am going to tell you better than what the book tells you. So here is what a differential is. Let me first write down how you write a differential, and then we will talk about what the significance of the differential is in practice. So a differential is very simple. If I have some quantity f, then the differential of f, which is written as df, is equal to the derivative of f with respect to x times the differential of x. If we have some other sort of variable, though, we can write it in that way as well. So for instance, we could write df is equal to the derivative of f with respect to u times the differential of u. One of the nice things about this is that it very naturally plays in with the chain rule, because then if u is a function of x, then du is equal to du by dx, and so then this differential becomes df by du by dx times the differential of x. So this differential stuff plays right into the chain rule. It makes the chain rule very, very simple. Now, what is the differential really doing here? Well, there's two ways to think about this. One way to think about it is this. What dx does, or what du does, what the differential of a variable does, or what the differential of an independent variable does, is dx, I'm going to need some space here to write this down. dx measures how fast x is changing in some sense. So if we say, okay, what happens to the quantity f when I start making x change at a certain rate? Well, the answer is dx measures how fast x is changing, and you plug it into this formula and it tells you, the rate of change of f is going to be equal to such and such in terms of the rate of change of x. So that is one way of thinking about what this differential is doing. A second way of thinking about what the differential does for you is that what we can say is, therefore, if x changes by some small delta x, then the change in f is approximately equal to f prime of x times the change in x, which is really just df if we replace dx by delta x. And we're going to be able to make this this idea of the approximation much more precise in a minute when we talk about linear approximations. But for the moment, I just want to observe that this is effectively one of the things you can do with differentials is you can say, okay, first off, they let us measure how fast one quantity changes when another quantity is changing at a given rate. But the other thing is that this means that if we have a small enough change to the independent variable, it tells us how much approximately the dependent variable is going to change. So in this particular example, x is our independent variable, f is our dependent variable, and this is what the differentials can do for us. Now, again, to really precisely define what a differential is takes a bit more work than this, and it really goes beyond, strictly speaking, what we're going to cover in this class. It gets into something called differential geometry, and it's a really fascinating field. I love it, but it's unfortunately, we would have to go into some technical definitions. But this is in practice what it comes out to be. And you can sort of think of this as the differential is what happens in the limit as you take these changes going to zero. That is sort of the intuitive way that people thought about differentials before the differential geometry concept came about. They thought of the differentials as meaning, okay, the small change in f, when we put a small change into x, is given by the differential of f. Now, let's talk for a moment about calculating some differentials. Well, we're really only going to talk about this for a moment because calculating differentials is pretty straightforward. If I have, let's say, f of x is equal to x cubed plus e to the x, then df is literally just going to be f prime of x dx, which is going to be 3x squared plus e to the x dx. And that is it. That's literally all you are doing. If you can calculate a derivative, you can calculate a differential. You just throw the differential of the independent variable on the end of it. Another way of sort of thinking about this is that the differential reminds us that x is the variable with respect to which we took the derivative. Now, that might seem kind of silly because we're usually in this class only working with one variable or one independent variable at a time. However, it's not that silly because often we introduce new variables, right? Like we introduce these various, like u in terms of the chain rule that we did. And so that's where this can become kind of nice, right? Because if I have, like, let's say that I say, okay, f of u is equal to cosine of u, and then u of x is equal to, let's say, x to the fifth. Well, then I can write df is equal to minus sine u du, and then I can write du is equal to 5x to the fourth dx, and then I get for free that df is equal to negative sine x to the fifth times 5x to the fourth dx just by plugging in u and du like this. So in this way, we can start off by thinking of u as the independent variable, but then if it turns out that u itself depends upon something else, we can just go ahead and calculate that differential and throw it in here. And everything kind of works out really nicely. So if nothing else, these differentials provide a really excellent bookkeeping device for keeping track of this stuff. And keeping track of this stuff this way is going to become especially useful later on when we start working on the other part of calculus. So there are really two halves of calculus in some sense. What we have been studying up to this point is what's known as differential calculus. It deals with derivatives and things like that. There's also what's called integral calculus, which kind of involves doing the opposite. And it turns out when we do the opposite, these differentials are going to show up once again all over the place. And being able to keep track of things like this is going to be important. And we will see that by the end of this semester, but not quite yet. So in part, I'm asking you to just look at how to work with differentials now, and we will see why they become so useful later on. Now, the other topic that we wanted to say here was about linear approximations. So let's talk about linear approximations. What is a linear approximation? The idea here is that I want to find, given some function f of x and a point A, what I want to do is I want to write down a function which is linear, which also is as close to f of x as possible as long as I am near the point A. So we want it to be linear and as close to f as possible near A. Now, why would you want to do this? Well, one reason you might want to do this is because linear functions are really, really, really easy to work with. I mean, you probably know that beyond constant functions, there's nothing simpler than a linear function. So often, if I'm only interested in a function if I only care about a function near a certain point, if I know that all of my work with that function is going to take place near that point, then maybe what I can do is I can say, okay, instead of working with whatever really complicated function I have, what if I just pretended the function were linear near that point? And maybe that will give me a good enough approximation for whatever I am doing. Well, what do we mean by as close to f as possible? What we mean by this is the following. First of all, we want to have LF evaluated at A. This should be equal to f of A. This means that LF of A is going to have to be equal to some slope times x minus A plus f evaluated at A. So that much is clear. But what else would we like to have happen? Well, what I would like to have happen is for the limit as h goes to 0 of f of A plus h minus, is this what I want? Give me a second to make sure this is really what I want. Yeah, I want this limit to be equal to 0. And in order to make this be true, well, what I can do is I can work out what this means. And to do that, and this is why this is confusing me, yeah, what I can do is I can say this is the same as f of A plus h minus f of A minus LF of A plus h plus f of A divided by h is equal to 0. There we go. Sorry for the confusion there for a moment. I got confused in my head, and yeah, everything is clear now. So I've just subtracted f of a and added f of a. But look at what actually this is. Adding f of a here, this is actually adding LF of a, because f of a and LF of a are the same thing. And what that means is that what I have written here, well, this is just f prime of a. And what I have over here, this is just LF prime of a, except it is negative. And so what we want in order for this limit to come out to be 0 is for their derivatives at a to be equal to one another. So we need f prime of a to equal LF prime evaluated at a. However, LF, this linear function, because it is linear, we will notice that LF prime at a, in fact, at any point, is just equal to this m. And what that shows me is that m needs to be equal to f prime of a. Okay, the prime disappeared inside of a parenthesis there, so I've drawn a new one. So what this tells me is that if I want to get the best possible approximation that I can using a linear function, then what I actually want to do is to write LF of x is equal to f prime evaluated at a times x minus a plus f of a. And this is the linear approximation to f of x at a. Now, notice that you're going to get different linear approximations at different points, but that's fine. The idea is that you can use the linear approximation near a certain point, but that's kind of it. So let's take a look at some applications of this. Let's start by saying, what if I wanted to compute a linear approximation for f of x equals sine x at x equals 0. Well, f prime of x in this case is going to be equal to cosine x. So that means if I take this formula for the linear approximation, this is going to be equal to cosine of 0 times x minus 0 plus sine evaluated at 0. But cosine of 0 is 1 and sine of 0 is 0, so this actually just comes out to be x. This is actually a really famous identity. Well, it's not so much I mean, it's sort of an identity. The linear approximation to the sine function at 0 is equal to x itself. What does this mean? And what I want to show you kind of geometrically or intuitively what this means, okay? So think about the unit circle. And I want to have sort of a big drawing here. So we're just going to draw a piece of the unit circle so that we have more space. What this is saying is that, remember, the sine of x, if this is my angle, well, actually, let me not label that as x because I'm using x for the angle. This height here is sine x. This arc length here is x itself, because remember, an angle in radians is actually the arc length of the unit circle that the angle, what is the word? The angle that it makes with the unit circle, the piece of the unit circle inside the angle, and I cannot for the life of me think of what that's called at the moment. But anyway, that piece of arc, that length is the angle in radians. What we are saying is you'll notice that for very small angles, if you move up or down the circle, you're basically just moving vertically. You're not really moving horizontally very much at all. And so the change in this height here is pretty much the same as the change in this arc length here. And that is what this makes precise. It tells us that the best approximation we can get for the sine of some angle is the angle itself. At least if we're interested in linear approximations near zero. This fact is used a lot in physics because there's a lot of things in physics where you can study something. For instance, when you talk about pendulum motion, if the pendulum is not swinging very far, you can use this kind of an approximation. It's called the small angle approximation, and it's good enough to derive some really important formulas in physics. And it has other applications too, of course, but there we go. Here's another example of using a linear approximation. So let's suppose that we want to estimate the square root of 99 using a linear approximation for square root of x at 100. So the thing about the square root function, right, you can't compute it exactly, or it's very difficult to try to get a good computation for this thing. You know, we really don't have a formula for the square root, in other words, that we can just write down. So how do you figure out approximately what a square root is? Well, the answer is you use a calculator, but if you don't have a calculator, then what do? One thing you can do is you can say, well, there are certain values where we can evaluate the square root exactly, and maybe we can use that to get an estimate. So what we're going to do is we're going to say, let's let f of x be equal to the square root of x, which is really x to the 1/2. Then what I can say is that f prime of x is 1/2 x to the minus 1/2, which is, of course, 1 over 2 square root x. So I can say a linear approximation at x equals 100 is going to be 1 over 2 times the square root of 10 times x minus 100 plus, why am I putting in the square root of 10? The square root of 100 plus the square root of 100. Now, the nice thing about this is that this is just 1 over 20 times x minus 100 plus 10. So now what we can do is we can evaluate this at 99. So we plug in LF of 99. This is going to be 1 over 20 times negative 1 plus 10. So 10 minus 1 over 20, which comes out to be 199 divided by 200. So there we go. This is an estimate for the square root of 99. Now you can check to see how close this gets. And you'll find it's actually it's reasonably close, really. Why did I say 199 over 200? 199 over 20. I have an extra 0 in there because I apparently just write zeros at random today. There we go, 199 over 20. So very, very slightly less than 10. And that's what we expect, is that this would be very slightly less than 10. But this gives us our best approximation for it, at least if we use linear approximation. And you can do this kind of thing with all kinds of other functions too. Cube roots, you can do it with exponentials if you happen to have a place where you can evaluate the exponential accurately. There's just all sorts of places where you can use these kinds of linear approximations. Although, of course, they're not necessarily as used anymore because we have calculators to do this stuff for us, so we don't need to use it as often. But one place where they still are used a lot is, you know, when people are talking about solving certain things where we're not just trying to maybe evaluate a function, but where we're actually trying to solve something in, for example, differential equations. We mentioned when we talked about applications, these idea of differential equations, where we have an equation that a function and its derivatives have to satisfy. Well, sometimes what you can do is your differential equation might be this really nasty beast. But what you might be able to do is you might be able to say, well, what if we just approximate it with some sort of linear approximations? And then when you do that, you might get something that's much more easily solvable. And as long as you are only dealing with values that are sort of close to wherever you do the approximation, you might be all set. Now, what is the relationship here between these linear approximations and these differentials? Why do we mention them together? Well, the reason is sort of silly in my opinion, because it's not really about what the differentials are. But the thing that I want to observe is that the change in the linear approximation is going to be equal to f prime evaluated at a times x minus a plus f evaluated at a minus LF evaluated at a. But f evaluated at a and LF evaluated at a, these are actually the same thing, so they cancel out with each other. And this leaves me with f prime of a times the change in x. So the change in your linear approximation is the derivative of f times the change in x. And this, the textbook thinks, looks like df. And it does look like df, except we've got a delta x in there instead of a dx. So it does kind of look like df. That f doesn't look like an f though, at x equals a. And yeah, that's true. So if you think of df as keeping track, or if you think of dx as actually keeping track of small changes in x, then yes, this makes perfect sense, and you can talk about it this way. But like I said, that is, although you can think of it that way and you'll end up with the correct answer, it's really not what dx is. Dx is not just a number expressing a change. And so I don't think it's good to get in the habit of thinking about it that way, even though you can sort of effectively make it work out that way. Because strictly speaking, dx measures, essentially what dx does is if I have, we're going to get into a slightly technical explanation here. Think about x on a number line, and I have some point A. Well, instead of thinking about changing x, what if I just express the way in which I want to change x? And what if I do that by using a vector? In other words, an arrow that points in a certain direction. Well, what does dx do? dx actually tells me the length of this arrow and the direction of this arrow. So if I say, this is how I'm going to change x, dx is what tells me the length and whether that is pointed in the positive or negative direction. And thus, yeah, it kind of does work out in practice that dx evaluated on this arrow, and this arrow is what is called a tangent vector, by the way. Yes, dx evaluated on this arrow does come out to be delta x. But I don't want you to think that df is literally the change itself, because it's not exactly the change itself. It's a little bit more, it works out that in practice you end up replacing df, or you end up replacing the df with delta. I keep saying df. You end up replacing the dx with a delta x. However, it's not because those are really the same thing. It's because that's what ends up happening when you evaluate dx on the tangent vector that expresses some change in x. The reason this is important to keep track of, it doesn't really make a difference here for us now, but later on it does make a difference that you really have that technical distinction down, okay? So you don't have to worry about what I just said about tangent vectors or anything too much, okay? You can ignore that and you will do fine in this class. But if you go on to do some higher stuff, you know, more classes like later on with mathematics, it may come back to where you really do need to think carefully about what does this differential really mean for you. And so that's why I just want to make sure that you're aware. Yeah, you can get away with just replacing dx with a delta x, but understand that there's a lot more going on there than just we can replace it. It's a sort of a special, it turns out we can do that, but that's not because that's fundamentally what it means. Okay, that was probably a bit confusing. So again, you can focus for your purposes in our course on just how do you do the computations. And fortunately, those computations are fairly straightforward. So I would like for you to take a look at all of the examples in your book. I think this is 3.8, but maybe it's 3.9, possibly 3.10. I don't remember the exact chapter number, and I don't have the textbook in front of me right now, but it's the section on differentials and linear approximation. And so make sure you take a look at those examples. They're all relatively straightforward, but it's good to see all of these examples to understand what sorts of, like, just to get some practice at seeing what's going on there. And I would even say these examples, at this point, when you're reading the book, try to do the examples yourselves before you read their solutions, because I think you might be able to handle just doing the problem, and you don't need to be shown how to do it. If you can take derivatives at this point, then these problems, like, you're already halfway through everything you need to know for these problems. And hopefully at this point you know how to take derivatives. One other interesting thing that I do want to observe here is that sometimes two different functions can have the same linear approximation even though they are very different functions. So if I want to do a linear approximation for tangent x at x equals 0, well, if I take f of x equals tangent x, then f prime of x is going to equal secant squared x. That means the linear approximation is going to equal secant squared of 0 times x minus 0 plus tangent of 0. However, tangent of 0 is 0, and secant of 0 is 1, so this just becomes x. But this is the same linear approximation that I got for my sine function. So it turns out that these two functions, even though sine x and tangent x are totally different functions, it turns out that they actually have the same linear approximation at 0. So that's a very interesting thing. Now, as a bit of an exercise, try to find the linear approximation for cosine at 0. I think you'll find that it's kind of weird, because what you're going to get, I will tell you the answer, but I want you to work out for yourselves how you got it. The answer is that the linear approximation is constant. It's just always equal to 1 for cosine of x at 0. So that's fine. The linear approximation can be a constant function. And once again, what that comes down to is the fact that on the unit circle, okay, that is not even remotely circular. Let's do a slightly better picture than that. On the unit circle, if I have some angle x, well, the cosine of x is this bottom side of the triangle. But the bottom side of the triangle is not really changing, because as I move this point up and down, the horizontal position isn't really moving. I mean, it moves a very, very tiny bit, but not really much at all. And so what this is telling me is that actually at 0, a little change in the angle doesn't really change my horizontal position. Or another way of putting this, the precise way of thinking about this is that as I'm changing x, at 0, I'm literally moving either straight up or straight down, which is only affecting the vertical coordinate. It is not affecting the horizontal coordinate. And that is why the linear approximation for cosine comes out to be 1. I will leave it to you to actually do the detailed calculation with the derivatives and the formulas and everything. I think you should be able to handle that. If you have any trouble, let me know and you can ask me questions. One more really quick thing I want to say before we wrap up for today, because I want to show you how this fits into the bigger picture. You could ask yourself, what if we wanted, instead of a linear approximation, we wanted to do a quadratic approximation, or a degree 3, or a degree 4 approximation. In other words, a linear equation, a linear function, that is really a degree 1 polynomial. So you can think of this as we're trying to approximate our function by using a degree 1 polynomial. Well, what if instead I try to approximate my function by using a higher degree polynomial? For that matter, I can go up to degree n polynomials. Well, yeah, you can absolutely do this. And when you do this, what you're going to end up doing is you're going to end up saying, well, the best approximation I can do is we require that our approximation, which I will call P of X, we require that P of A is equal to our function at A. We require that P prime evaluated at A needs to be equal to F prime of A. And in general, we require that all the derivatives up to degree n, sorry, that's my P side, should be equal to the derivatives of F evaluated at A. And these conditions turn out to specify a unique polynomial of degree n that approximates my function f. And these polynomials form what is called the Taylor series for f at a. So it turns out that these are really, really important. And in Calc 2, if you go on to take Calc 2, we get to study these in detail and understand their full significance. Because it turns out we can do things like estimate how far off is the error going to be when we use one of these approximations. We can also do things like we can say, what happens if we sort of take a limit as we let the degree of the polynomial become arbitrarily large? Well, it turns out that for nicely behaved functions, like e to the x or sine of x, it turns out that the Taylor series ends up converging in the limit to the function itself. And so, in a weird way, you can sort of think of e to the x. It is not a polynomial function, but the Taylor series allows you to almost think of it a little bit like an infinite degree polynomial. That is very imprecise, and you shouldn't literally think of it that way, but as sort of a guide, an intuitive guide, you can think it's a little bit like that, because it is equal to the limit of a bunch of polynomials. However, to make sense of what that limit means, we need to talk about what is a series, what do you do with all this stuff. So there's technical details to work out, but that's roughly speaking what's going on. And it's not actually that difficult to see what you need to work out the coefficients to be in order to make this work. But I'm not going to go into the details right here because we've taken up enough time and we're not really going to be doing Taylor series in this class. But the last thing that I want to say is a linear approximation is a Taylor series for f that has been truncated after the first degree. So technically speaking, if we truncate at degree n, we say it's the Taylor series truncated at n, but the Taylor series is all of the possible things, and it becomes complicated. So it's something that you'll see in Calc 2, but I just wanted to tell you, these linear approximations really are only scratching the surface of how do we approximate things. And it turns out that kind of in the limit, these approximations can be made arbitrarily accurate, and eventually you can recover the function from them if you allow your approximations to become bigger and bigger and bigger and get better and better approximations. Okay, so what we're going to be tackling next week is we're going to be jumping into various applications of differentiation. These applications, we've seen some in the natural sciences and in the social sciences and in finance and things like that. But it turns out that differentiation is also really useful for doing things like optimization problems, like how do I maximize profit? Or how do I minimize the materials that I need to build a certain object? All of these types of questions can be answered using calculus. And it turns out that these ideas end up playing a big role later on in physics too, because it's not just about engineering questions about optimization. It turns out that all of physics, all of classical physics at least, not quantum physics exactly, but all of physics can be derived by asking certain optimization questions. More complicated optimization questions than what we're going to be able to do with calculus with a single variable, but the same idea. And so we're going to be getting into all of that sort of stuff next week. In the process, we're going to have to develop some new properties of derivatives and how they interact with the behavior of functions. And this will also lead us to see how using derivatives, including the higher order derivatives, I can actually say a lot of very useful information about what a function has to look like. So I'm going to be able to do things like sketch a very accurate picture of a function by hand, just by using a function and its derivatives. So all of that stuff will come in next week. But in the meantime, make sure to take a look at your homework and let me know if you have any questions or anything, and I will see you later.